going to be very basic. You can look at the histogram of the residuals. So these are the residuals associated with the dependent variable or earnings. We can also look at the normal probability plot, which is something that we want to see as a nice, almost perfectly linear effect across the two axes, and we'll look at that plot in a minute. And I think another one that people commonly do is they use the Z predictor variable as X and the Z residual variable at Y, and this is going to create a scatter plot, and we hope to see that that plot will basically not reveal any patterns in the data. Basically, you want to see a bird's nest. You just want to see scattered data that seem to be randomly distributed across your bivariate plane in the scatter plot. And we'll take a look at that in a minute. The sample size is only 25 in this, so it's not the greatest sample size for a linear regression period, but especially for doing analyses associated with the assumption of heteroscedasticity, it's pretty tough to actually test it in a really sophisticated, meaningful way. But we'll still do it here just for demonstration purposes. Go to continue, and I think that's all we're going to do here. You can save various residuals if you wanted to get really sophisticated in how you test your homogeneity of variance assumptions. But we're not going to do that here. I just want to keep it simple. And click OK. And here's the output for the regression analysis in SPSS, and we can see that the descriptive statistics in the first table, mean earnings, is $545 weekly earnings. Now this is back in the 90s, so that's not accurate anymore in 2011, but back in the 90s or late 90s, which is I suspect where I simulated these data from, weekly earnings was $545 with a pretty big whopping standard deviation of 401. So that means there's a lot of variability in earnings, which is what we'd expect in reality. You know, a lot of people earn, some people, a small percentage of people earn a really huge amount of money, but most people are lower than that, substantially so. Now, education, the average is 13.56, so a little more than high school, and the standard deviation is 2.93. In the next table, we've got the correlations, and we've got, well, with a single correlation, and it's a 0.423. So there's a moderate correlation between how much education someone has and how much they earn on a weekly basis. But I suspect this correlation is not as big as most people hope it to be, particularly people who are entertaining the idea of going into university and learning more and having more years of education under their belt. Does it really increase your earnings that much? Looking at this correlation, I'm be thinking not by a lot, like not by a huge amount. We'll see in more precise detail what the values are exactly. Now, this is variables entered, removed. That's more from the multiple regression type table that will be meaningful here. It's not. Model summary. I think what's important here is you get the R value, which is repeated from a previous table, and you get the R square value, so 17.9% of the variability in earnings, weekly earnings, can be accounted for by years of education. So less than 20% of the variance in earnings is accounted for by education. So it's a very meaningful predictor, but it's not accounting for a huge amount. And when you adjust it, this is interesting in SPSS, particularly when your sample size isn't very large. And with 25, that's not very big. And we can see that SPSS has estimated the adjusted R square at 14% of the variance, so less than 15% of the variability. And the difference between R square and adjusted R square becomes smaller as your sample size gets larger, and I would say anything over 100, and the difference between adjusted and R squared is going to be pretty trivial. And I guess I don't want to say too much about it, but basically, if you have only 2 people in your sample size, an N of 2, you will get perfect correlation every single time. Just by necessity, because if you've got any variability in your data, one's going to be higher than the other. So you're either going to get a perfectly positive correlation or perfectly negative correlation. That might sound very odd to people, but if you calculate this yourself by hand, just an n of 2, you will always get a perfect correlation. So this adjustment is based on this phenomenon that as you have very